Today we're going to talk about section 8.2, which is matrices. This is probably something new to some of you, and so we're going to try to go in a little bit of detail, but this book does assume that you have covered this in Algebra 2. So if you look through the book and you listen to the lecture and you still are having lots of questions, you need to make sure you come and ask them. A matrix is a rectangular array of numbers. You can see an example of one here. They're put in these little brackets, and we just list our numbers. Each number is called an entry. An entry is designated with this little notation here, A with two little subscripts, where I is the entry's row and J is the entry's column. So for example, in this matrix here, our entry A21 means row 2, column 1, which is 4. So our entry for A21 is 4. The matrix's size is said to be m by n, or the number of rows by the number of columns. So there's 3 rows in this one and 2 columns, so it's a 3 by 2 matrix. Mostly what a matrix is used for is data collection. You may have seen the movie The Matrix. The only reason that even works to be called that is because of the containers where they kept people. It were some kind of rectangular array. I guess you could call that a matrix. Or maybe they were talking about the computer, the fact that computers use matrices a lot. But it really doesn't have a whole lot to do with it. So let's see what we can figure out about matrices here. 2 matrices are always equal if each individual entry is equal. So if we have a matrix here, and this one is entry row 1, column 1, and then we'll go ahead and give this one a number, and this one and this one. So we have a 2 by 2 matrix here. This is row 1, column 1, row 1, column 2 is our entry is 1, and then we have row 2, column 1, our entry is 5, and row 2, column 2, our entry is 7. And if we want that to be equal to a different matrix, let's call this matrix A, and we want it to be equal to matrix B, then what we do, we look at matrix B. If this is what matrix B looks like, and we have some variables in here. We've got this one, we don't know what number that is, and this one and this one. This is entry row 1, column 2, and this is row 2, column 1. We don't know what those are. If we want these to be equal to each other, then whatever's in this spot has to be equal to what's in the same spot in the other matrix. Whatever's in this spot has to be what in the same in the other one. Whatever's in this spot has to be the same here, and whatever's in this spot has to be the same here. So we look at those, and we see that that means that A11 has to equal 2, and we see that B12 has to equal 1, and we see that B21 has to equal 5, and the 7s were good. So that means for this to be true, this is what we need. So if you're asked, what do these entries have to be so these matrices can be equal, this is what we're asking for, a list of each entry and what it has to be so that we can have them equal. Now, you can add and subtract matrices, but in order to add and subtract matrices, you have to have them the same size. So let's say we have a 2 by 2 matrix. Then we want to add it. It has to be another 2 by 2 matrix. 2 by 2 matrix. I can't talk and write at the same time. Sorry. If we have these, when we're adding and subtracting, all you have to do is go with the individual pieces. So if we're looking for the answer one, what's going in row 1, column 1, then we have the first one plus the second one, and that's our new entry for that section. And then for the other part, 2, plus 5, 3 plus negative 3, and 4 plus negative 7. So we take each, this is row 1, column 1, so we look at row 1, column 1 plus row 1, column 1. So we end up with an answer matrix that's negative 9, 7, 0, negative 3. If we want to subtract, it's virtually the same thing. Let's say we want to subtract these. Now again, when you're adding and subtracting, they have to be the same size. This is a 3 by 1, this is a 3 by 1, so we're good. So again, we look row 1, column 1, row 1, column 1 gives us our row 1, column 1. Again, row 2 and row 3, so that we end up with an answer matrix like this. So for adding and subtracting, as long as they're the same size, you can do it, and you just take individual entries and put them together and then put them in that same space. Not too hard? I hope not. If you have more questions, make sure you ask. Remember, addition is commutative because we would still be able to switch this and we would have negative 10 plus 1, and we'd be able to still get the same answer. Now let's see, an additive inverse. Now you know if we have 5 plus negative 5, that equals 0, and these are called additive inverses. And this is the additive identity. Well, with a matrix, we have the same thing, except instead we have two matrices, matrix A, and then another matrix, which we'll designate as negative A, and that's going to give us the same numbers but different signs, and you end up with the 0 matrix, where whatever size you have, it goes 0 in every single space is 0. And that is your additive inverses for matrices and your additive identity for matrices. So example, if we have this matrix, it's a 3 by 2 matrix, and we want to have its additive inverse, then that means all the signs are different, but the numbers are the same, so that when we add it together, 1 plus negative 1 gives us 0, 2 plus negative 2 gives us 0, 5 plus negative 1, or 5 plus negative 5, gives you 0, negative 1 plus 1 gives you 0, 7 plus negative 7 gives you 0, 9 plus negative 9 gives you 0, and you end up with a 0 matrix, which is the additive identity for matrices. So adding and subtracting matrices, not that hard. Just look at the individual pieces and make sure you remember about the inverses and the identity, because sometimes we need those. Now multiplication is a little bit more difficult. Multiplication by a scalar is not that big a deal. A scalar, when you're talking about matrices, is just a plain number that's not in the matrix. If we have a scalar multiplied by a matrix, all you do is multiply each individual entry by that number, and you get a new number, a new matrix. So a scalar just is kind of like the distributive property. It just distributes to everything, and that gives you a new matrix. Now, multiplying matrices themselves is a little bit more difficult. When you're multiplying matrices, you have to be very careful about the sizes. For example, if we have let's say a 2 by 2 matrix, then this matrix is 2 by 2. If we want to multiply it by another matrix, then that matrix has to be 2 by something. The middle numbers, when you're lining them up, the middle numbers have to be the same. So we could multiply it by, say, a 2 by 3. And that would work. The middle numbers here have to be the same or you can't do that. Now, why is that? Well, when we multiply matrices, what we're looking at is we look at the row and the column, and that gives us our new entry. So for example, with this first one, if we want this entry that's row 1, column 1, then we're going to have 2 times 2 plus -1 times 3. Then if we look at the next column on the same row, we have row and column, and we multiply. We have 2 times 1 plus -1 times -1. And then for the third column, we do row and column again, and we have 2 times 5 plus -1 times 0. Now you can see how I multiplied the first one here times the first one here, and then the second one times the second one, and add those together, and that gives me my new entry. Now for the second row here, if we want the second row with the first column, then we multiply the second row, and we multiply those entries just like we did before, and then add them up. And I'm out of colors, so we'll have to just go with the same ones, I guess. So if we have this one with this one, we have 5 times 1 plus 0 times -1. And then if we want the second row, third column, we'll have 5 times 5 plus 0 times 0. So look this over, pause it, and make sure you see how I got each of these individual pieces here when you multiply it. That's why these middle numbers have to be the same, because you're multiplying row times column to get your new row column entry. So once you have that, we have 4 minus 3 is 1, 2 plus 1 is 3. Make sure you're checking my math here. 10 plus 0 is 10. 10 plus 0 is 10. 5 plus 0 is 5. And 25 plus 0 is 25. Now, notice your answer is going to be row by column, the outside ones. The middle ones have to match, and your answer is going to be this outside size here, 2 by 3. So that's multiplication of matrices. Row times column gives you the row column entry. Row times column gives you the row column entry. Make sure you look at this carefully and work on it, and look at the examples in the book and make sure that you know how to do that. Now, if you recall, when we multiply, we also have inverses. So if we have these two numbers are multiplicative inverses, and 1 is our multiplicative identity. Now, with matrices, you can also have identities for multiplication. And the way we write that is A times, we call it its inverse, and the identity matrix is I, and the identity matrix has 1s all along the diagonal and 0s everywhere else. So, Ones down the diagonal, zeros everywhere else. And that gives you an identity matrix. So you end up with 1 and zeros all up the. So 1 down the diagonal, zeros everywhere else. It has to be square, which means that it has to be a 2 by 2 or a 3 by 3, same equal rows and columns. We know that if we multiply a number times the identity, we get that same number. Same thing happens with matrix. If you multiply a matrix times the identity matrix, then you're going to get that matrix back. We're not going to do too terribly much with these right now. We'll work on these a little bit more, but just make sure you know what the identity matrix is. Now, the last thing I want to point out is we've been working with systems of equations. So if we have a system of equations, you can also write that as a matrix. So let's say we have this system. And we want to write that as a system of matrices. What you do is you have your coefficients, and these are all the x's in the first column, and then all the y's, and then all the z's, coefficients for each of them. And what you're doing is you're multiplying it times the variables. Remember, when we multiplied, it was this first row is what ends up multiplying times, or the first column ends up multiplying times this first one here. So we had to have 3x plus 2y minus 3 or minus z. And then we have our answer matrix here. Now, look at this, multiply this out using the technique we just did, and make sure you can get back to those equations and you understand how those are set up, because in 8.3 we're going to use that a lot. The way we write this in matrix form, we say it's matrix A times matrix X equals matrix B, because this is our variable. We're going to use those for systems of equations, and we're going to use them for solving those systems too. So make sure you recognize that. We have run through matrices very quickly. Make sure you have read the whole section thoroughly, watch this video a couple of times, make sure you take good notes, especially if you've never seen matrices before. Please make sure you are really thoroughly prepared with lots of notes and plenty of questions when you come into class.